The most dangerous message in statistical software may be converged. It tells us the algorithm stopped according to its rule. It does not tell us that a finite maximum exists, that this is the highest peak, or that the data determine one unique parameter setting.
But it says success.
Algorithmic success is only the beginning. 3 geometry questions decide what the estimate means. Start with 4 heads and no tails. Holding those observations fixed gives the curve shown here over probabilities from 0 to 1. As the candidate probability moves right, the likelihood keeps rising. The displayed score is the derivative of the log likelihood. It stays positive everywhere inside the allowed interval. So there is no interior 0 to solve.
Then where is the estimate?
At the endpoint, probability 1. The maximum exists, but the usual interior rule that the score equals 0 does not apply. Symmetric uncertainty approximations also need special care at a boundary. The best fit can also escape entirely. These binary outcomes are perfectly separated by the input. Logistic regression makes the curve steeper by increasing its slope coefficient. Every increase makes all 6 classifications more confident, and the displayed log likelihood moves closer to its upper limit.
So how large should the slope be?
For every finite value, a larger one fits better. The optimum lies only at infinity, so no finite maximum likelihood estimate exists. An exploding coefficient is a diagnosis, not a reason to let the optimizer run longer. A complicated likelihood can have several peaks. At each marked peak, the gradient is 0 and the curve bends downward. Those conditions establish a local maximum. They do not compare its height with distant parameter values. The right peak is higher, so only it is global. A well-behaved Hessian at the reported answer cannot certify that no better peak exists elsewhere. Launch the same optimizer from 4 dispersed starting points. The first update moves each point uphill. The next update carries it deeper into the basin where it began. Each path settles at a nearby peak.
Can every run still report convergence?
Yes, compare the final likelihood values, not just the success messages. Multiple starts expose competing basins, although they cannot prove that every basin was found. Separate peaks can also have exactly equal height. This mixture uses 2 bell-shaped components to make the teal distribution. Swap the component labels and the colored bells exchange names, but the teal distribution does not move. The likelihood is therefore unchanged.
Are those 2 different explanations?
They are 2 coordinate labels for one observable model. Equal modes caused by label symmetry are different from getting trapped on a lower peak. Sometimes multiple maxima merge into an entire ridge. Consider a Gaussian regression that accidentally includes the same input feature twice with 2 separate slope coefficients. Collecting the repeated terms reveals the problem. The predicted mean depends only on the sum of those coefficients. The observations can see the sum, but not how it was divided. Every yellow point in the coefficient plane has slopes that add to 4. The plot on the right shows the resulting fitted line. Move along the ridge. The first contribution grows while the second shrinks, yet their total, the fitted predictions, and the likelihood remain fixed.
Then which coefficient is the right one?
The data have no answer. There is a continuum of maximum likelihood estimates. Identifiability names this issue. A model is identifiable when any 2-parameter settings that generate the same observable distribution must actually be the same setting. Here, 2 distinct coefficient pairs generate the same conditional distribution. The Hessian exposes a 0 curvature direction along the ridge. More observations with this exact duplicated feature sharpen the likelihood across the ridge, but never along it. If the features are nearly, rather than exactly, duplicates, the flat ridge becomes a long, shallow contour. One maximum may now exist, but a tiny change in the data can move it a long distance along the weak direction. The individual coefficients swing while the 2 fitted lines nearly overlap. A more informative design may help, but until then, stable predictions can coexist with fragile parameter interpretations. A profile likelihood makes a weak direction visible. Hold the parameter of interest fixed, then maximize over every other parameter. That operation is the equation at the top. As the vertical slice sweeps across the surface, each yellow point records the best likelihood still available. Together, they trace the one-dimensional profile on the right. A sharp profile isolates a narrow range. A shallow surface produces a flat profile, revealing that many values remain nearly competitive. Match each diagnostic to the geometry. For existence, inspect parameter bounds and watch for estimates that keep diverging. For globality, use dispersed starts and compare their final likelihood values and predictions. For uniqueness, inspect profiles and curvature in every direction. Then simulate data, refit the model, and ask whether the distinctions you want to interpret can actually be recovered.
Can a penalty or a prior fix the ridge?
It can choose a point on it. A prior adds information in a Bayesian update. A penalty adds a preference to the optimization objective. Either can produce a useful unique fit, especially for prediction. But the observed data likelihood remains flat. The selection came from the added assumption, not from new identifying information in the observations. Before interpreting a maximum likelihood estimate, ask whether it exists, whether it is global, and whether it is unique. Convergence describes the algorithm. The geometry determines what the estimate means.